Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abdullah Al Masri. I am a mechanical engineering student. So today we will study the automatic control chapter 2, and we will solve some of the problems that related to the chapter. First of all, we will start with 2.4 section, which is electrical network transfer functions. Electrical network transfer functions, which is in this section, we will formally apply the transfer function to the mathematical modeling of electric circuits, including passive networks and operational amplifiers circuits. Subsequent sections cover mechanical and electromechanical systems. Rather than writing the differential equation first and then taking the Laplace transform network chapter 2, modeling in this chapter will be the frequency domain Laplace transform. We can draw the transformed circuit and obtain the Laplace transform of the differential equation simply by applying Kirchhoff's voltage law to the transformed circuit. We summarized the steps as two steps. The first step, redraw the original network showing all time variables such as Vt, It, and the Lt. Also, in second step, replace the component values with their impedance values. This replacement is similar to the case of DC circuits, where we represent resistors with their resistance values, and we will see these steps by start solving some problems related to this section. So we will have the first example, transfer function single loop. So the problem, find transfer function relating the capacitor voltage VCS to the input voltage Vs in figure. So the figure is clearly show the electrical circuit, which we have the voltage supplier, and we have the impedance and capacitor, and also we have the inductor or inducting element. So the solution in any problem, the designer must first decide what the input and output should be. In this network, several variables could have been chosen to be the output. For example, the inductor voltage, the capacitor voltage, the resistor voltage, or the current. The problem statement, however, is clear in this case. We are to treat the capacitor voltages as the output and the applied voltage as the input. Summing the voltages around the loop, assuming zero initial conditions, yields the integral differential equation for this network as. So the integral differential equation, it will be as L dit over dt plus Rit plus 1 over C. So the L, it will be the inducting, and the R is for the impedance, and C for the capacitor, and integral from 0 to t. I tau d tau equal Vt. This is the first statement of this solution. The second one, we will change the variables as the I. We will change the I for Q, and then we will start solve this differential equation as from the voltage charge relationship for a capacitor in table 2.3. We will take the transfer function from the table and replace it in this solution, substitute it, and we will have LC d square VCT over dt square plus RC dVCT over dt plus VCT equal VT. So the last two steps, which is we will have this equation LCS square plus RCS plus 1, because we took VCS as a common factor. So after that we will divide the VCS over the VS. So we will have on the other side 1 over LC over S square plus R over L multiplied by S plus 1 over LC. And this is the final solution, and this is the output of this electrical circuit problem. The second section in this chapter, which is the translational mechanical system transfer functions. Mechanical systems parallel electrical networks to such an extension, the real analogues between electrical and mechanical components and variables. Mechanical systems, like electrical networks, have 3 passive linear components. 2 of them, the spring and the mass, are energy storage elements. 1 of them, the viscous damper, dissipates energy. The 2 energy storage elements are analogous to the 2 electrical energy storage elements, the indicator and capacitor, or inductor and capacitor. The energy dissipator is analogous to electrical resistance. Let us take a look at these mechanical elements. So we will see this example to see clearly the mechanical components. So we can see here we have the spring, and with the K, which is the stiffness of the spring. We have the viscous damper, and we have M, which is the mass. So the problem, find the transfer function XS over Fs for the system of figure. So the solution began by drawing the free body diagram as shown. Place the mass, all forces felt by the mass. We assume the mass is traveling toward the right, so it goes right to the right hand. Only the applied force points the right. All other forces impede the motion and act opposite direction. So the first function we will write M multiplied by d square xt over dr square plus Fv, which is the force of viscous damper, dxt over dt, and plus the spring, which is the K, the constant of the spring or stiffness of the spring, kxt equal ft, which is the final force, or the final the resultant force of this system. So here we can see the forces that acting on the mass. We have A and B. The A is a free body diagram of mass spring and damper system. B is transformed free body diagram. And also, if we continue, we will take the Laplace for this equation. So we can take first of all common factor, which is the common factor here is xs in every single one. We have xs, so we will take it as a common factor. So we will reach to the ms square plus fvs plus k common factor xs, and then we will divide the xs over fs, and we will find the resultant is 1 over ms square plus fvs plus k. That is the resultant of this problem. We will go to the other section, which is the rotational mechanical system transfer function. Having covered the electrical and transitional mechanical systems, we now move on to consider the rotational mechanical systems. Rotational mechanical systems are handled the same way as transitional mechanical systems, except that torque replaces force and angular displacement replaces transitional displacement. The mechanical components for rotational systems are the same as those for transitional systems, except that the components undergo rotations at transitional. So these are the components. We have the first one, the spring, and we have the torque angular velocity formula, which is T or tau T equal K integral from 0 to T omega tau d tau. The torque angular displacement Tt equal K theta T, and the impedance is K, as well known for the spring. The viscous damper, we have Tt equal d omega T, but the torque angular displacement for the viscous damper is d theta T over dt, and the well known is ds, which is the damper. And last one, the inertia. The inertia in the system, which is J Tt equal J d omega T over dt, and the torque angular displacement Tt equal J d square theta T over dt square, and well known as Js square. So we will go to the example to make it more clear. Example 220, equations of motion by inspection. The problem writes the Laplace transformation of equation of motion for the system shown in the figure. So this figure, we have damper, inertia, spring, second inertia, and also second damper, and third inertia and third damper also. So we have only one spring, 3 dampers, 3 inertia. So start with the solution. We will have here the sum of impedance connected to the motion at theta 1 minus sum of impedance between theta 1 and theta 2 minus sum of impedance between theta 1 and theta 3 or theta 2 equal sum of applied torques at theta 1. So after this step we will have another step, which is simplify the equation, and then the last equation we will reach to the js square plus ds square. We will see it more clear. Okay, we can see it here. J1s square plus D1s plus K theta 1s minus this one, all of it equal to 0. So this will be the final output of this system after all simplification. And we can go back for here. So we have also transfer functions for systems with gears. So the gears is a main components with a mechanical engineering field. So we have to know how to deal with and control with the gears in the mechanical systems. So gears provide a mechanical advantages to rotational systems. Anyone who has ridden a 10-speed bicycle knows the effect of gearing. Going uphill, you shift to provide more torque and less speed. On the straightaway, you shift to obtain more speed and less torque. Those gears allow you to match many applications. The gears allow you to match the drive system and the load to trade off between speed and torque. For many applications, gears accept backlash, which occurs because of the loose fit between two meshed gears. The drive gear rotates through a small angle before making contact with the meshed gear. The result is that the angular rotation of the output gear does not occur until a small angular rotation of the input gear has occurred. In this section, we idealize the behavior of gears and assume that there is no backlash. So we will see the problem to understand this concept. So here we will find the inertia, damper, and another inertia 2 and damper 2, and we have spring. So we have here the free body diagram. So we can go through the solution. It may be tempting at this point to search for two simulations questions corresponding to each inertia. The inertias, however, don't undergo linearly independent motion, since they are tied together by the gears. Thus, there is only 1 degree of freedom and hence one equation of motion. Let us first reflect the impedance, the inertia 1 and damper 1, and torque 1 on the input shaft to the output as shown figure. So we will write the equation of motion of the damper 1, inertia 1, and torque 1 as JE S square plus DE S plus K multiplied by theta S equal to T1, which is the torque, S N2 over N1, which is the number of meshed gears between two gear, where JE equal J1 N2 over N1 all square plus J2, DE equal D1 N2 over N1 all square plus D2, and KE equal K2. We will solve it for theta 2 S over T1S. So we will find this relation theta 2S over T1S. It will be equal N2 over N1 over GES square plus DES plus KE. The last section in this chapter will be electromechanical system transfer functions. A motor is an electromechanical component that yields a displacement output for a voltage input, that the mechanical output generated by an electrical input. We will derive the transfer function for one particular kind of electromechanical system. So to make it more clear, we will see so this is the problem. Given the system and torque speed curve, so begin by finding the mechanical constants Jm and Dm in equation. So the total inertia at the armature of the motor is equal, it will be as Jm equal Ja plus Jl multiplied by N1 over N2 all square, and we will substitute these variables with their values. So Ja, which is equal 5, Jl, which is equal 700, and N1 equal 1, N2 equal 10 all square. The result it will be 12. And the total damping at the armature of the motor, it will be as Dm equal Da plus Dl multiplied by N1 over N2 all square. And also we will substitute the variable as the values, so the result it will be 10. And this is the schematic diagram, which is we have the impedance, we have the inertia, we have the damper, and we have the electrical current, and also we can find the KT over RA, which is equal to torque over EA. So this is the relation, and we can continue to find the KB, which is EA over omega with no load. So the omega with no load equal 50 and EA equal 100, so the KB equal 2. And also theta M over EA, it will be equal 5 over 12 over S multiplied by S plus 1 over 12 multiplied by 10 plus 5 multiplied by 2. So this is the resultant value in this problem. So now we can back to the so now we will have the last section, electric circuit analogs. In this section, electric circuit that is analogous to a system from other discrepance called an electric circuit analog. Analog can be obtained by comparing the describing equations, such as the equations of motion of mechanical system, with either electrical mesh or nodal equations. When compared with mesh equations, the resulting electrical circuit is called a series analog. When compared with nodal equations, the resulting electrical circuit is called a parallel analog. So we will see the example to make the concept more clear. Converting a mechanical system to a series analog. So here we have to convert it to series analog, not parallel. So the series analog, which is the mesh equation. So we will have to find the mesh equation. So analogs to electrical mesh equation after conversion to velocity. So the mesh equation we have here ms plus fv plus fvs multiply by fv1 plus fv2 all plus k1 plus k2 over s. So this is the equation, and after that we will simplify and take common factor, and we have the another equation. And here we have the schematic diagram of this problem. So here we have the M1, which is the inductor, we have the capacitor, we have the impedance, and also here we have impedance, we have inductor, we have a capacitor and impedance, and this is the voltage supplier. So that was the equation for mesh, which is the series analog problem. And thank you for listening.